A special class of partial differential equations are called quasi-linear partial differential equations. One example of such equations are the Poisson equation, which we have discussed, especially the Laplace equation when f of x, y is equal to 0. Generally, a quasi-linear partial differential equation is an equation which is linear in the highest order of derivatives. For second order partial differential equations which are quasi-linear, we have they are of this form. So we have some constant a multiplied with the second derivative of the unknown variable u with respect to x, plus, and we have some constant here, 2b, multiplied with the derivative of u with respect to x and with respect to y, and plus a constant c multiplied with the second derivative of u with respect to y. And on the right hand side of the equation we have some function which is not necessarily linear, but is a function of the spatial coordinates x and y. Actually, it does not need to be spatial coordinates. It can also be the time t. So instead of using xy, we can replace it by y. And it's a function of u and the first order derivatives of u. One example, or let us just say some words about classification of quasi-linear partial differential equations. They are elliptic if this condition is satisfied, that the constant a multiplied with c minus b square is larger than 0. One example of this is the Laplace equation. It's called parabolic if AC equal the square of b is equal to 0, and hyperbolic if AC minus b square is less than 0. And we have 3 classical examples of elliptic, parabolic, and hyperbolic equations. The typical example of elliptic equation is the Laplace equation. For parabolic equations, we have the heat conduction equation as an example, and for hyperbolic equation, we have the wave equation. Let's just now show that the Laplace equation in fact is elliptic. You know that the Laplace equation takes this form. So if we go back to the general definition of general description of the quasi-linear partial differential equations, we see that this a must be 1, b must be 0, and c must be 1. So, and on the right hand side we just have the function f is in this case equal to 0 for all values of x, y, u, and so on. So in this case ac minus b square is in fact 1, which is larger than 0. So it's indeed an elliptic equation according to this definition. So let us give an example now of the heat, or show that the heat conduction equation is parabolic. We know that the heat conduction equation is given by ut equal k square multiplied with the second derivative of u with respect to x. So in this case we can, let us just change the variable t to y. just to see that we have this exact same equation. We have to do this because in the general description we have no t. So in this case, the derivative of u with respect to y is equal to k squared multiplied with the second derivative of u with respect to x. So let's just rewrite this equation. We see that in this case k squared must be this a in the general description of the equations, the quasilinear equations. B must be 0 because we don't have such terms. We don't have these terms either, the second derivative of u with respect to y. But we have this term, u, the derivative of u with respect to y. And we now see that this is now the function f. So f is in this case just equal to uy. And we note that the k squared must be a. So k squared is a positive number, and c is 0. So a times c is 0, and b is 0 as we told, so this must be equal to 0. And this shows that we have a parabolic equation. We can do exactly the same for the wave equation. We just have to replace t by y and do the same, so we realize in this case that the wave equation is hyperbolic.